Hello, everyone. Welcome you all to the online forum on climate change technologies. Today, we have Professor Saifur Rahman as our second speaker of the day. He's an IEEE Life Fellow, and he was the president of IEEE in 2023. Currently, he is the director of Virginia Tech Advanced Research Institute. With this brief introduction, I would like Professor Rahman to start his presentation, and then we will take questions at the end of the presentation.
Thank you, Mitrudip. Thank you, everybody, for attending. I'm happy to be here. I heard the last 10 minutes of Claudio's presentation. Interesting. I am touching the same subject to some extent. But if you look at my title, Promoting Technology to Achieve a Sustainable Climate, two things, technology and sustainable climate. How do they help each other? Just in a preamble, I work a lot in climate resilience field. I go to the UN conference on climate change every year. I'm going tomorrow, in fact, to Brazil, and I'll talk about IEEE's contributions in this field. I'm saying this because we need to know IEEE must have a seat at the table where decisions are made. Because when I go to COP meetings, I went to Azerbaijan this past year, before that Dubai, before that Egypt, and all of that is fine. People talk about problem. We need to talk about solutions. This is my approach. So having said that, let me move on then. So this is my building. It has a solar panel set on the roof and EV charging in the basement. So you can come to my building, charge your car with solar power. This is very interesting. And then go on. The reason I'm showing this not for this building, I am showing here my personal website, srahman.org. The reason I show this, because this site has this presentation PPT already published. So no need to take pictures, just listen to me carefully, and you can go to that website here and go to presentations tab, and you'll see this slide deck already there. So this is how I do my business. So you can go to that same presentation tab on my website and say what I gave last night, what I gave last week, what I gave last month, all of that is there. So you'll see how we are involved in climate resilience, a climate change field. Now the technique. So we talk about carbon emissions, talk about carbonization, talk about decarbonization. Like we just heard the previous speaker talk about when the GHG gas will flatten out, emission increase, when begin to drop the carbon emissions. But before we talk about decarbonization, we have to understand what is carbonization so we can tackle it. This is where I start. So it is a challenge for climate sustainability. And today's world, about 70% of the carbon emissions impacting the environment coming from CO2, 70%. Others, next is methane, and then NO2 and fluorocarbons. So 70% is carbon dioxide, that is methane. Now, what is carbonization? Look at this picture, this graph. This is atmospheric carbon dioxide measurement over last 800,000 back. If I look at the data, the CO2 emissions in the North Pole, why North Pole? North Pole has no trucks, no cars, no planes. So all the air is pure. Pure meaning it has CO2, hydrogen, NOx. This has no pollution, no particles, no PM2.5. This is why our reference is carbon emissions or carbon intensity on the North Pole. And the reference is here at the bottom of the screen. So you could ask me a question. This is 2025. How do I know what was the CO2 concentration in the atmosphere on North Pole that many years back? No electricity then, no computers, no sensors, no nothing. How do you know? Good question. If you think about it, it's not that difficult. North Pole is cold, so air has moisture. Air has moisture. When moisture becomes snow, it takes some air with it, obviously, right? Otherwise, it'll be ice. So moisture gets cold, becomes snow, falls on the ground, and stays there because it's below zero all the time, below 0 centigrade all the time. So snow is building every year, right? Building, 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 and over time, that snow becomes ice. We know from past history how many years it takes for the ice sheet to become 1 meter thicker, 1 meter worth of new ice. We know that number. Now we can calculate how many meters of ice has formed over the last 800 or million years. Data also exists million years back. I'm just starting at 800,000. We know that. Now you drill a hole in the ice sheet, go down that many meters, then you know you have reached the ice sheet that existed 800,000 years back. If you know that information, you can pick up a ball of ice from that depth and bring it out. Put it in a freezing compartment, take it to the lab, and let it melt. Now imagine that ice is moisture and air formed ice, snow and ice. So now you know that cube of ice you picked up from that depth has frozen water, moisture, and air with it. Now in the controlled environment in the lab, you let it melt. It'll melt. As it melts, the air comes off. You hold the air in a chamber, and through spectroscopy, you can analyze the chemical content of that air sample that is that many years old. You know what is the CO2 concentration in that air bubble, what is the hydrogen concentration, oxygen concentration, all of that. Not difficult, just take some effort. Now, I know the air sample I picked up, which is that many years old, has in this case 180 parts per million CO2 concentration. We know that. I can go back 800,000, 700,000, 600, 500, 400, up to zero. Zero is 1950 level. I'll tell you why we stop at 1950. Anyway, look at that graph. The CO2 concentration moved between 180 to 300 at the most, 300 ppm, parts per million, never more than that. In the 1950s, we began to burn coal in large scale in power plants, large scale. Coal is the primary cause of CO2 emissions. And that level shot up to 420. Now it's 454 or so today. So this is the long-term concentration of CO2 over time. So we'll talk about Paris climate change in a second. So this is more recent data, more recent. I'm not going back 800,000 years. I'm going back 1750 till now, 2020, 2025, till now. Two lines. The purple one, atmospheric CO2 concentration parts per million, ppm. And the blue line, the CO2 emissions per year, per year. So look at that purple line. It starts at 280 or so, beginning late 1800s, it begins to rise. And up to 1840, 1850, CO2 emissions not measurable, like zero. So then it began to creep up, late 1800s, and then 1900s, and then it shot up after 1960 or so because of the heavy burning of coal in power stations. Now, what happened in late 1800s or mid 1800s? Mr. James Watt, his statue is here in Glasgow. I was there. I took this picture myself. He was born in Glasgow 1736, died in 1818. He is the man who invented the steam engine. Steam engine ran on coal. Steam engine, you may not have seen yourself, but you have read in books. The train locomotives, the black ones that pull the train before it became electric trains, ran fully on coal. So we can blame Mr. James Watt for CO2 concentration if he did not invent the steam engine, we would not burn that much coal in power stations, in ships, in other vehicles, trucks, and mining equipment, and so on. So this is why began to grow in the late 1800s till 1930 or so, not that bad. We have 5 billion tons per year. And as the power industry picked up and ships began to plow the oceans, it has today is about 43 billion tons per year emission. I'm giving you every slide has some reference points. Those are the sources where I picked up these numbers if you want to follow up and do more research. Okay, now that is carbonization. We have seen now what caused the CO2 concentration in the atmosphere to increase dramatically. Now the impact, what is happening because of carbonization, global warming, and the like. This is a data showing the global temperature change. My reference is 1850, starting and ending at 2024 September. The multiple sources where data comes from, point I'm trying to make, even there are 4 or 5 sources, they're all saying the same thing, or 6 sources in fact, all saying the same thing. So the global mean temperature is 1.54 degrees C plus minus 0.13, 24 September. The Paris Agreement, 2015 Paris Agreement, said we should not allow the temperature change from prehistoric time till now to exceed 1.5 degrees C target. We already exceeded that already. The target said reasonably below 2.0 degrees centigrade. What is reasonably below? 1.5. Now, 1.5 is gone. We're looking at not to exceed temperature change more than 2 degrees centigrade. So that's the challenge. Now, it has impact on the water bodies also. Because of the heat, you have more seawater turning, making moisture, and the available seawater is not flowing down as much. So you're getting more dry conditions downstream where you have rivers, India, good example, China, then Bangladesh, parts of that part of the world, the Himalayan water supply is being reduced. So 2023, the driest year for global river in over 3 decades. And as a result of temperature rise, the water flow in the rivers are decreasing. So last bullet on the screen, 3.6 billion people face inadequate river or water access. This is meaning not salt water, normal water that you can drink. So if we don't do something, the 3.6 billion people are short of water. It becomes 5 billion people with short of water over time. Okay, now impacts. I'll give you some country examples. Upper left is Bangladesh. This is 2 years ago. Yeah, that's right. Lower left is California, Hawaii. Upper right is India, New Delhi, and lower right is China. It's happening not only in low-income countries. Los Angeles had a big fire this year, and China had flood, so on and so forth. Example. So let's look at more details. January 2025, the Palisades fire, people were killed in this fire earlier this year. And it tore through neighborhoods in a matter of minutes. People could not flee fast enough. You can see the house catches fire, and the fire trucks don't have time to get there. House burns down in a matter of minutes. This is Bangladesh, August 2024, about a year ago now. Flooding, people have leave their homes and go to higher elevations. It's very sad. This kid, lower left, had a buoy on his neck so he doesn't drown, and carrying a container with bread. This kid had no role in global warming. He did not burn coal to make electricity. He did not drive a car. He did not eat a ship, but he is suffering. Lower right, these two girls are sitting on logs and floating in the water. And upper right is a woman carrying her child, walking through through the road, which is flooded. And upper left, same thing. This is very sad, very sad. Now in India, New Delhi, May 2024. It was so hot, people did not have drinking water. So the city governments sold or sent water trucks, and people put all these pipes out to get the water to drink. Forget about washing and other things. Just drinking water became a scarcity in New Delhi a year and a half ago now. This is Spain. Spain is not known for flooding, not known. See, in Spain, city road are inundated. The sad part is the water was so fast and so much water, it washed away cars. They dumped these cars one over the other. Car is not a light vehicle, but its buoyancy and pressure did that in Spain 2024. Those are flood examples, lot of water. This is drought, lack of water. Two examples, one upper left in Italy, Po River. On the right is China, which is in Yangtze River in China, Chongqing, China. The water is gone. As a result, you can walk across the water, across the riverbed, not have need a bridge to cross over. This is the example of drought. Again, we are talking about climate change, not just global warming, climate change. So global warming is a part of it, but flood, drought, fire are the examples of global warming's impact. So now as an electrical engineer, power engineer for that matter, I focused on electricity production. Globally, about a third of the emissions CO2 come from the power sector, power stations, third. Another third comes from transportation, almost 40% now. Transportation, mainly cars and other vehicles and ships and planes. And remaining third comes from industry, cement, steel making, buildings, and so on. So third, roughly. So I, as a power engineer, want to focus on my industry, which is responsible 1/3 of the emissions of CO2. Now, where can we go to reduce emission in the electrical power sector? First, use less electricity and energy efficiency. This is the low-hanging fruit. If you can manage, like air conditioning load today, I can raise the room temperature from 21 degrees to 23 degrees centigrade. You would not feel the difference. By going the delta T of 2 degrees centigrade, I can save 10% or more electricity that is not needed to run the air conditioner as frequently. So this is the low-hanging fruit. That's air conditioning. Lighting also, I can dim lights and reduce the energy consumption, power consumption by reducing the light intensity. That's the fastest and cheapest way. Second is, we know today globally over 1,000 coal-fired power plants in operation, 1,000 or more. We cannot just shut them down tomorrow. It's not possible. Even today, India, China are building tens, dozens of coal-fired power stations. My point is, yes, you have to build coal, but you need to be more careful, use more efficient coal plants. I'll give more example coming up. Hydrogen, which I talked about in the earlier session, is a storage technology, but still not fully mature. Number 4, I said, accept some nuclear. Why do I say accept? Because of accidents like Fukushima, Chernobyl, in the US, 3 Mile Island, nuclear has bad press. There are now new technologies, I'll give example in a few minutes, which are not so dangerous. Number 5, promote cross-border power transfer, meaning every country must not have to be fully independent of energy source beyond its border. People buy power from other countries. More example coming up. Next is electrification. Yes, we can do electric vehicle, heat pumps, to reduce coal consumption in power stations. And finally, more important, promote more renewables. All examples are coming up in a second. Now, first of all, customers controlling buildings can reduce electricity consumption. I has an example. Energy savings from air conditioning control can be 10 to 15% by just raising the temperature by 2 degrees or maybe 3 degrees, no more. Savings of electricity from lighting control, in a room like this or in an office room or a lab, if you dim the light from normal up intensity, 20% down, you cannot tell the difference the light was dimmed. But by doing that reduction in light intensity, you can save 15%, 20% electricity. But you have to do some pre-planning to make it happen. That's lighting control, energy efficiency. Example here. If you replace incandescent lamps with LED lamps, you save about 80% plus. The same lumen for light from incandescent, if that is 100, same lumen from an LED lamp will be like 10 or 12 watts. So that's 80% plus saving electricity, same light. Because we as building user, homeowners, we don't care about electricity, we care about what you get out of it, right? The building conditions, like we need so much lighting, not electricity. Keep in mind, not electricity. We need so much light. We need so much heating and cooling. Keep that thought in mind as we go forward. Now, yes, this is a coal-fired power plant in the Netherlands. It is ultra supercritical steam power plant, coal driven, but efficiency more than 45% as opposed to 40% for normal coal-fired power stations. Carbon capture storage. Yes, we will burn coal. We'll run ships with diesel engine and so on. Then, since you will generate CO2 and that goes in the sky, there are now technologies to capture that carbon and store underground so that it doesn't escape. It is not scaled yet, small scale and pretty expensive, but it is a technology worth looking into. Hydrogen. Hydrogen is a fuel. You can run an IC engine using hydrogen directly. I've seen a text in Berlin recently where it says IC engine running on hydrogen. Other things like fuel cells are possible, but this is a technology evolving. On the other side of hydrogen's value is storage. Like you have solar daytime, nighttime demand is high, no sun in the night. So you will make hydrogen electrolysis, store it at night, and then use that hydrogen in a IC engine or fuel cell or vehicles. So hydrogen storage to me have to come together. You cannot just make hydrogen. If you make it, then what? What do you do with it? That is example I have to see. Fuel cells, IC engines, and the like. Next is advanced nuclear technologies. Why I'm saying this? As I said before, the large-scale 1,000 megawatt or higher power stations, nuclear, are out of fashion. They're extremely expensive. Very few countries except China are building those today, and they have the risk of accident. But there are now new technologies, advanced technologies. As the example is small modular reactors. Small modular. What small? 100 megawatt or less. And they are modular, they're smaller, can be built more quickly in a factory. Typically, a nuclear power station is everything done on site, takes about 10 years to build because of from digging the ground till loading the fuel and running the nuclear part of the power station, make steam, and then drive your generator. That's a 12-year cycle. SMRs will be 2-year cycle. One other good thing is when you have a 1,200 megawatt nuclear power plant, one plant coming online, suddenly on the grid, that much power goes in, injecting that much, like overnight. But if you had an option of building in stages, like 100 megawatt each, as demand grows, you'll build them. So over time, yes, 10 years later, you have all of those 1,200, but they are not all coming online at the same time. This is other benefit of small modular reactors. Okay. One example here. This is a 60 megawatt electric capacity of a nuclear power plant, small. Height is 20 meters, diameter 2.7 meters, and capacity, the weight is 590 tons, 4.95% enriched uranium, like a typical nuclear power station. Look at the right side picture. You see this is at the bottom, the red part is your nuclear component. That is the heat source. Then you have a passing water from the two containers on the right and left. Water becomes steam, goes up, and the generator on the top that is driven by steam and making electricity. So all of those, nuclear source, steam engine, electric generator, all in one box. If you look at a typical large 1,000 megawatt nuclear power plant, there's separate units. Nuclear containment building is nuclear reactor. Then it pass water through it, or it gets heated, come to the next building, has steam produced. That steam high pressure will drive a generator, and then you have transformers getting power out. So good thing here is you dig a hole in the ground, 20 to 25 meter deep, 3 meter diameter, and stick this thing in the hole. That's and then cover the lid, and you have 3 wires coming out, 3-phase power coming out, 60 megawatt or so. Simple and less. It's all self-cooling and nothing to blow up because it's all contained in one box. So next is cross-border energy transfer. As I said before, no country is fully independent from electrical source within the borders. The saying goes, no transition without transmission. So here you go. There are many ways to do cross-border power transfer. 3 examples here: bilateral, multilateral, unified. US buys quite a bit of electricity from Canada. That's bilateral. US buys and Canada sells. Multilateral, one country can sell to multiple countries. Example, Europe. France sells to Portugal, to Spain, Austria, and the like. There was a big blackout earlier this year in that part of Europe because a lot of solar went out suddenly, but this transfer of power from France was not triggered quickly enough. That's multilateral. Unified is like EU grid. It's one grid, unified. All these 12 or 14 countries on that grid supply power, receive power in normal operation as one unit. So this is the example of cross-border power transfer. Some examples of this cross-border power transfer. This is Gulf countries, 6 countries that interconnected from Kuwait to UAE, to Saudi Arabia, to Qatar, Bahrain, and then to Oman on the right. So this is an example of where you will see these countries are buying and selling from each other. One side benefit is solar is big now in Saudi Arabia and UAE, and we have seen solar, they have no snow issue there, but sandstorms. Sandstorm can quickly cover solar panels, reducing output by 30% or so. If a sandstorm, or when a sandstorm hits UAE, Dubai and that area, power drops. Simultaneously, Saudi Arabia is not getting the same sandstorm, so their power is fine. They can then feed the demand in UAE area from the Saudi solar. It's not day-night issue, it's a reliability issue. That's why they built this line. An example is Laos, Thailand, Malaysia, Singapore interconnection called ASEAN Power Grid. Laos has a lot of hydro, but no market in the country. They're selling power through Thailand into Malaysia and to Singapore. Again, cross-border power transfer. Everybody benefits. Singapore has no room now to put new power stations. They don't. So they're getting power from Laos and Malaysia and their own gas-fired generation. So, one more example. Vietnam is a country, if you look at the map, very long country. So the northern part of Vietnam has demand, all the supply in the south. If you have to build a long power line from southern part of Vietnam to the North Vietnam is expensive. And north part of Vietnam border on the other side is Laos. Laos has a lot of hydro, so they have decided to buy hydropower from Laos and serve the northern Vietnam load and not bring power from the southern part of the Vietnam country. Now, electrification. Here, talk about electric vehicle, heat pumps. So, electric mobility, people talk about this, but if you think deep, it's not that easy. If and when in the US all vehicles become 50%, we have to quadruple the US power generation, quadruple 4 times to serve that load. That is going to be a problematic situation because that much extra electricity means more power stations, more transformers, more substations, more power lines. I can guarantee you, public would not accept it. I would not like 4 times the power lines crossing my backyard or bigger transformers in my backyard. I just cannot tolerate. So what happens? I do not know. But this is a challenge. Don't get too excited. Everything electric. It has to come from somewhere. Solar not enough to run your electric vehicle. So as young people, students in this audience, think about this. So find a way to find electricity not put from a long distance location like nuclear and bring power to your backyard. Problem we're facing now, the AI data centers. We live in Northern Virginia, has a lot of data centers. This is problem we're facing today. Public is opposed to building new transmission lines to bring power to serve the data center. Now, this is the EV. Heat pumps. Heat pumps meaning you're replacing gas or oil-fired boilers that you use at home. Some case, England is a big example. US also. Replace that with heat pump. Fine. Issue is there enough heat pump being produced in the US or UK or Germany or whatever to replace all the boilers? The answer is no. That takes time. Other bigger challenge is skilled manpower. People who work on boilers cannot put heat pumps. They're two different technologies. So the issue is how you train the new manpower to make that transition possible. So again, it is not just technology, it's manpower and market forces will be helpful. So very quickly, a few examples. Wind power, we know wind is big in China, India, US to some extent. New market is growing. Saudi Arabia is getting a lot of interest in wind right now. Example here, 400 megawatt wind power station came online in 2022, saving million tons of CO2 per year when they make electricity from oil as opposed to from wind. So 400 megawatts saving electricity source from oil and gas. Pretty cheap, 1.99 cents per kilowatt hour. That's cheaper than coal, oil, and diesel for sure. That's one example. Other example in Saudi Arabia is 600 megawatts coming in line next year, 2026, will save 3.2 million tons of CO2 per year. Cost even cheaper, 1.56 cents per kilowatt hour. So wind and solar are not only clean, they're cheaper than coal and oil sources today. Some solar examples, two kinds of solar. On the left is solar photovoltaics with the tilting angle. On the right is solar thermal. These are a parabolic dish, glass. You put a tube in the focal point of the glass surface, and then the glass will reflect sunlight into its focal point where the tube is located, carrying water. Water becomes steam, and then in the back of my picture here, you take the steam, pump it to the power station where steam generator will use this steam and run a electric turbine. So another big solar in Saudi Arabia, 600 megawatt AC, one location. And Next is even bigger, February 25 online, 2000 megawatt in one location. In many countries, land is an issue, like India, Bangladesh, because of the agriculture activities. But here in the desert, doesn't matter. In the US, Virginia and Maryland has local state laws. You cannot put solar panels on land that is used for agriculture. Cannot do that. So we don't have a lot of land to cover up with solar panels. Anyway, these are examples. So now IEEE, what is happening in IEEE in terms of climate change? We have a program that I lead on IEEE's Sustainable Climate Sustainable Climate Program. We have a website at the bottom, sustainable-climate.ieee.org. If you look there, it's a lot of examples. I'll give you an example right now that we are talking about biodiversity and clean technology examples and so on. This is another example of this site. What is our mission? Our mission, as you know, IEEE's logo, advancing technology for humanity. How we are doing this? We are using technology, efficiency, solar, wind, and others to replace fossil generation. And as a result, we're helping to reduce carbon emissions in the global scale. So this is our logo, technology for a sustainable climate. If you go to the website, a lot of information there. Please be my guest. So this is another example of solar. I'm just clicking through the cover landing page. One example I'll give you, very important. We do a conference every year in Geneva, Switzerland. It's called IEEE ITU Symposium on Achieving Sustainable Climate. What is ITU? It's a UN agency, International Telecom Union. They talk about digital access globally. So we are working with them because they have a challenge also. If you promote digital access, you have to provide electricity to run their equipment, obviously. And where's the electricity coming from? Typically, diesel engines in remote areas. That is not something we can morally support in the long run. So that conference at the bottom of the screen, isasc.ieee.org. If you go there, you'll see the meeting happening in Geneva this year, next month, in fact. If you want to go there, go to the website and request to be invited. So you can attend this meeting at your own time. Same example of the conference. If you go to the isasc.ieee.org website, you'll see this program, see who is speaking, what topic is being discussed, and you can learn more about IEEE's role in achieving sustainable climate going forward. That'll hopefully make you feel proud that IEEE is doing something, not just writing conference papers and standards. We are also helping to save the climate by producing technology solutions to reduce carbon emissions. So one more example here, we are very active in many areas. When I was president, I commissioned a book, Inspiring Technology. This book has history of 34 major breakthroughs in our history of electrical engineering, beginning 1880s and till now, which is very interesting. Talking about solar, but many other things are there. If you want to, a book is free online. It's an ebook. This long URL is a page you can go directly to read the book, or to be simple, you go to IEEE.org website and type these two words, inspiring technology. Just type it and the book will show up. And you can use it, read it, and make comments on what is happening globally going forward. That's it for now. So thank you very much. Again, keep in mind, my website, srahman.org, has this slide deck already published. With that, let me stop here and take questions if you have any. I'm done. I'm stop sharing now.
Thank you very much, Professor Rahman. That was really a very nice talk on climate change. So we have few questions already in the chat box.
You can read
But I'll start. Yes. So you can hear me, right?
I can.
Yeah. So I'll start with a very basic question. because you have shown the CO2 emission in your initial slides, and I can see that the CO2 emission is still, I mean, that is still rising. So we are yet to reach to that saturation level. So I'm just curious, does that mean that even after a lot of research on clean solutions, we are still far from having an effect of those technologies on CO2 emission, or we are very soon going to reach that saturation level?
Very good question. I am following climate change conference in Brazil starting next Monday. In fact, I'm going there tomorrow.
Okay.
It has been reported by UN that the growth of CO2 emissions growth has stabilized. That means not growing anymore, stabilized.
Right.
Does not doesn't mean it's not happening, but not steep rise. That has stopped. It's flat, rising but flat. 42 billion tons per year. That number is flat. That was
Mm,
33, 35, 37, 30, like this. It's flat 40. It's a good sign. But we could bring
mm,
it down to almost zero by the end of the century, which is a challenge. So, what has to be done to make it to zero? We have to suck out this carbon dioxide in the sky. Doesn't vanish. It lives for 100 years plus. That means you have to do the carbon capture, CCS, and ocean has to absorb more. So this is a
mm,
big challenge. Many countries, US as an example, have said by 2050 will be net zero emissions. That means we're not emitting any more than zero, net zero. That means
mm.
net zero doesn't mean zero. Something will grow. We are sucking some other from the air.
Nice.
US
Okay.
2650, China 2060, EU 2050, India 2070 target, net zero.
Okay. Nice. Yeah. Okay, so we have another question which is related to hydrogen. So where do we see hydrogen having the most impact? Is it transportation, energy storage, residential heating, or production?
No, residential heating not possible. We're going to pump the hydrogen to my house. That's not going to happen anytime soon, like natural gas today. My forecast is it will be in IC engines
Mm,
in large scale over time. You cannot, as is in my talk, I said, if you talk about batteries, if you talk about batteries, that is going to need electricity. And as I
mm,
said, US will not have enough electricity supply to serve all cars with batteries. That's why
mm,
hydrogen-based cars make sense. As an example.
mm, mm,
Number three is fuel cells.
mm,
I have seen in China fuel cell trucks long
mm,
600 kilometers or more, and they carry
mm,
hydrogen in the truck. It's a heavy duty vehicle, so weight is not an
mm,
issue. That's an example of long haul truck will be hydrogen based and ICE engines.
mm. Okay, so we have another question, which is how can emerging technologies be leveraged to effectively monitor and reduce global carbon emission? What role will advanced sensing technologies like sensors, IoTs, networks, satellite imaging play in the real-time monitoring and proactive regulation, atmospheric and industrial carbon emission?
Example is methane. A lot of methane leaks from
Mm,
methane mines, power, the tubes, the pipelines, and at the usage point.
mm,
2023, Dubai COP had a policy on monitoring methane leak, monitoring, that's the example. They're using
mm,
sensor satellite data to monitor where
mm,
methane coming out. If you monitor it, you know where it's coming, then talk about you seal the leaks in those cases. So this
mm,
is an example of using technology for methane emission. CO2 it can be easily sensed. In my lab, I can sense CO2 level in the lab. But issue is not sensing, we know what is happening. Issue is controlling. So we can see, you can have sensors which will monitor the effect of these technologies to suck CO2 and see how much is being really reduced. You need to
mm,
measure them outdoors. That would be
mm,
a sensor technology application.
mm. Okay. So now there is another question which is more on policies, like how, say, political decisions can actually influence the project to deal with climate change. So any comment on that?
Yes, it's a very important thing for me. When I go to the conferences, today China has the highest CO2 emitter. China number one, India number two or three, US two or three, depending on how you count. When US tells China, you are the biggest polluter of CO2 in the world, it's true if you look at country. But you cannot compare US with 350 million people and China 1.23 billion people. Cannot compare. When you count CO2 emissions per person, China like number 11, not one. US is number one per person, number one. This is the fairness issue. So this is a
Mm,
debate. US says drop it, China says you are, if we had billion plus people, you'll do the same thing. So this is why we have all these plans in UN missions that pay for carbon reduction, pay.
mm,
Brazil is the host of the COP this year, next week. Brazil Amazon forest, and they're cutting the forest to make land for agriculture. Once you cut the forest, you stop the sink, like trees collect CO2. Brazil said, sure, we would not cut the trees, but I must compensate my farmers who have no land to cultivate. So who will pay the money? So Brazil has said now this week that build a $50 billion fund primarily given by countries which have produced CO2 last 100 years. And then you can pay our farmers or find other technologies to grow rice on a more optimum level and not cut the trees down. This is other example. And
mm,
other example is developing countries need money to go solar. Developed countries have not producing much today, but they produced last 100 years. If I look
mm,
at, I didn't show that slide. Data shows 20% of the countries in the world has produced 80% of the CO2 in the sky. 80% produced by 20% countries, which is not rich countries, EU, Japan, US primarily. So
mm,
should be reversed. Other 80% of the countries, poor India, Bangladesh, China, Vietnam, Cambodia, all of that, where do they go? Okay, give us some money. We'll put electric furnaces, not boilers. We'll put LED lights. We'll put battery cars. We need money. So this is the debate going on today.
mm. So just a follow-up question to that, you mentioned different geographic location and the effect of climate change or the consequence of climate change are so diverse in different areas. Somewhere it's drought, somewhere flood. So what do you think that how to prioritize research, or is there a technology that one should prioritize to combat the climate change, or how do we decide that? Is there anything that you can
Yeah,
comment on?
that's what I started with, carbonization and decarbonization. So
Mm,
carbonization is happening naturally because of our behavior, things we do. So to decarbonize, I give you six, seven examples: efficiency, nuclear, renewable, cross-border power transfer, and
mm,
then electrification. So those,
mm,
how do you build a plant which is more efficient, like coal example in Netherlands, 45% efficiency. So my
mm,
focus is there's no silver bullet, no one thing.
mm,
Incremental changes in many different areas. So that's where I'm saying look at any opportunity that is relevant to your country and do
mm,
the best you can. Starting with methane leak, for example. Methane leak. That is going to happen, but no one technology. You have a portfolio of solutions, seven items, and pick one that you want to focus on and move on. Example,
mm,
New York State buys 1,000 megawatt plus hydropower from Quebec, Canada. They have
mm,
two choices: buy from Canada or build a coal power station, same
mm,
electricity. They chose to go to Canada. So
mm,
always make that cross check. What are my solutions, options? and what will be the best way to save the climate.
Mm, okay. Yeah. So with this, I think there are no more questions in the chat box. So I would like to thank you, Professor Rahman, for this very interesting talk and this question and answer session. So with this, we are closing this session. And Charlie, if you have any announcement, please go ahead.
Sure. I'd like to thank everybody who joined us today. We've already posted some of the talks. We hope to post today's talk soon. We'll take a break now so that Saifur can go to COP and
Okay.
start again on December 1st. I pasted a few of the links in the chat there, and that's there. Let's see. Again, I want to thank everybody and ask people to pass the word about the talks, and see you on December 1st. Ravinder?
Yeah, thanks, Charlie, and thanks, President Rahman. It was very interesting talk. I think we'll take a break at this time for upcoming COP, and we will reconvene in December.
For Charlie's benefit, I'll take pictures in COP where IEEE is active and share with you. You can promote that after the fact.
Excellent. Excellent.
Thank you, guys.